Hello everyone, this is Rohan Meshram, and in this session we would be still talking about some basic exercise in protein structure visualization. Our objective today will be to perform tasks like coloring, tasks like measuring and labeling. We would be using SPDBV or deep view to perform this task. Okay, and we would be using the same model of lysozyme from a white of hen egg for this purpose, as we have used in our previous videos. Okay, so well, let us begin by starting our SPDBV program. And when you start this SPDB program, as I have already mentioned, it is always better that you always set your preferences to default by using this button, reset to default preferences. So by doing this, what you are doing is that you are setting uh, all the settings to the default mode as such. Okay, so that every time you begin, we all will begin with the same set of preferences. Okay, so sometimes it might happen that you might change some preferences. Okay, so in order to begin from a fresh start page, we would I usually kind of do these things, and I would advise you to do the same. Okay, always set your preferences to default so that everything would work very fine. Okay, so now let us begin with our favorite molecule 1HEW. Okay, so you can either drag and drop it to load it into your SPDB. Well, there are other options as well. Okay, so if you don't want to do this, there is other options, like you can go to file and then open PDB file, right, and then go to this desktop. Okay, on this desktop you might have your protein molecule, locate it over here and hit open. It will also open. Well, another way round of loading the protein molecule is by, well, say for example, if I have opened this thing and here you have the last molecule that you have loaded is usually located over here. So we have last time loaded 1HEW from desktop, therefore we would be using the same molecule. You can also load it from this list as well. This list kind of gives you an idea as to what were the molecules that you have loaded in a previous file. So you can use either of the three ways that I have just mentioned for loading the protein molecule. Okay, so one more thing that I would like to mention that I have somehow not told you in my previous video is that there are a few popular representation for representing a protein. So by default, your deep view shows your protein molecule in wireframe representation. This they call it as wireframe representation. Some people also refer it to as line representation. Okay, so if you go to this display, okay, and render in solid 3D, what you see is called as stick representation. Okay, and if you hide this stick and right click in this ribbon column, anywhere in this ribbon column, what you see is ribbon representation. Some people also call it as cartoon representation. Okay, so there are different representation in which your protein molecule uh, can be shown. Okay, so these are just three popular representation. Your protein molecule can also be shown in surface representation, but discussing surface representation is way out of scope of at least this tutorial. Maybe I will create some another video for analyzing surfaces of the protein. Okay, so stay tuned to my lecture series. Okay, so now again let me go to display and let go the stick representation. So now we are at the default wireframe representation, which is colored by this CPK. The model is said to be colored by CPK. Okay, so this CPK color representation was named after three scientists that proposed this CPK representation. That C from CPK stand for Robert Corey, P from CPK stand for Linus Pauling, and K from CPK stand for Walter Colton. Colton, sorry, Walter Colton. Okay, so these three guys together proposed representing the molecule with different color, represent the atoms in the molecule with different color, and hence in their memory we call them as CPK representation. Okay, so let us begin with coloring. So the main objective of our today's discussion is to let you know what are the different ways in which you can color your protein molecule in order to study it effectively. Okay, so now your deep view provides many different ways to color the model. Okay, and I should tell you that coloring is not something that you should take lightly when you are dealing with molecular modeling. Okay, so to state in otherwise, color is not a trivial matter in molecular modeling. You should try learning these things very carefully. Okay, so why? Because colors can reveal structural, chemical, and comparative features very vividly, and thus by coloring your model properly, it can help you to keep your bearings during complex operation. You can keep your tabs as to what is happening where. When you try to compare the protein, or when there are complex operations that are needed to be done. Okay, so in that context coloring can be very useful. Okay, so now to start out with, well, let us select the entire molecule. Well, let us display the entire molecule by hitting enter on your keyboard. You can display the entire molecule, and you can kind of center the molecule by using this zoom center button. Okay, so now what we want to do, what I want to do is that I don't want this side chain for my demonstration for a while. Therefore, if I right click over here, the side chains would go away. Okay, so now this is the model of one HEW that is selected, that is displayed, that is centered, and we don't want the side chain. That is how I want my molecule for time being. Okay, so I have also turned off the ribbon, or if you have if you have been playing with hydrogen bonds or any other features, please remove it appropriately. Okay, so now what we want is only the backbone of our protein molecule colored in CPK, showed in wireframe without side chain. So that is what we want. Okay, so now the very first task that can be done in coloring is that you can use this color menu from this main toolbar. Okay, so you can go to color, and if you color it by secondary structure, let us see what happens. Okay, so by doing this, this deep view will color helical residues in red, beta the residues that are present in your beta strands and eventually in beta sheets, they are colored in yellow. Okay, and all the other residue except beta strands and alpha helices are colored in gray. Okay, now you should also notice that these colored are displayed in these small squares besides each residues that is listed in your control panel. Okay, so this is where it shows as to what residue is colored in what color as such. Okay, so you should also notice that there is this color menu uh, present over here. We will come to this color menu in a while. Okay, for time being, you should notice that this color menu command colors all the group regardless what is selected. Okay, so well, say for example, if I select these residues, okay, and then I again go to color and color it by secondary structure, it would still color everything. Okay, so whatever color command you use from this main menu, indicate that it would act upon the entire model no matter what is selected over here. Okay, so if you want to color something in your protein model for entire protein structure, then you should use these commands. So this is what I want to say. Okay, so we would again do the same thing. Okay, now if I use this color and color our model by secondary structure succession, as you can see over here. Okay, now you can observe the same thing. Although the residues 5 through 12 are selected over here, but the coloring has been done for the entire model. That is what I want to show you guys. Okay, so now when you color it by this secondary structure succession, as we have already done, your deep view would color helices and strands. Okay, but with this command, color would reflect the order of each structural element in the overall sequence of residue. In other simpler words, this deep view colors the first element of secondary structure as violet and the last element of secondary structure in a shade of red. Okay, so and whatever the residues that are present in between this violet and red, well, those would be colored as per the colors that are present in your visible spectrum. Okay, so in this way the resulting model that you see over here, okay, the resulting model that you can visualize over here is that it becomes easy for you to follow the chain through the protein. Okay, so in this way you can easily locate as to what is the first secondary structural element in my protein structures. Okay, so the residues that are colored in a shade of blue or violet are the N-terminal residue, and the secondary structural element that are colored in the shade of red over here, well, these are the residue that are present on the C terminals. Okay, so in short, deep view assigns as many shade as needed for the number of secondary structural elements that are present in between the N terminus and C terminus according to your visible spectrum. Okay, and as before, your deep view would assign the color of gray to the elements that do not belong to secondary structural elements like alpha helices and beta sheets as such. Okay, now what we will do, there is another coloring scheme over here. So what my take home message is that by coloring by secondary structure succession, that is from here, color by secondary structure succession, you would be able to locate as to what is the N terminus of my protein, where is the N terminus of my protein, and where is the C terminus of my protein. This task becomes handy in such operations. Okay, another way around is that you can color your protein by chain. Okay, now if you color the model by chain, what DeepView has done is that it has colored the entire model in yellow color, as you can see over here, as well as in your control panel. Okay, so now if there were more than one chain in this model, okay, each chain would be then colored with a different color. Okay, so therefore the coloring by chain provides a good contrast to the colors if there are multimeric proteins. Okay, so well, say for example, proteins can be multimeric, it can contain more than one chain. Okay, so now by coloring by chain, then you can identify as to which one is chain A, which one is chain B. Okay, so on and so forth. So by coloring the chain in this yellow color, well, now it will become very handy to provide some contrast for the side chains that we are going to color next. Okay, so I want you to do one more thing. Okay, well, first let us select non-polar amino acid residues. Okay, how can we do that? To select only non-polar amino acid, you can go to this select menu. Okay, then you can select this group property, go to this group property. Okay, and select this non-polar. Well, now just note in your control panel that nothing is selected, right? And when I go to this select and then group property and then non-polar, after clicking over here, you would notice that some of the residues in your control panel would turn red. Look, so by selecting this, that means you have selected all non-polar amino acid residues. Okay, now what we will do is that we would show only the side chains of non-polar amino acid residues. For doing that, you can use this side heading in your control panel. You can click over this side heading and it would only display the non-polar amino acid residues side chain. All other amino acid residue side chain are not shown over here. So now by when you click on this heading side, what it has done is that this action will add side chains to the selected residues only. In our case, we have selected the non-polar amino acid residue. Okay, now you should notice that besides this color option or besides this BS that is shown over here, I don't know if you can see it properly, you have got this BS and you have got a small triangle over here in your control panel. Okay, so if you click over here, it would show you another small menu that would pop up or that would appear. Okay, so now this little menu in the control panel color menu, it would determine whether color command affects the backbone or whether the color command affects the side chain or whether the color command would affect both backbone and side chain, or if you want to color only ribbons or if you want to color only label or if you want to color molecular surface. Well, you can decide as to what is needed to be colored over here. Okay, so now from this menu, let us select this side chain. Okay, when you select the side chain, now you should note that previously there used to be BS over here. Now it has changed to only S. Okay, so that note that now this S letter S has appeared next to your color. Okay, so what do this indicate? This indicate that whatever subsequent coloring commands that we are going to use, that would affect only the side chain and not the backbone. Okay, so this would indicate that whatever coloring command that we will do now, that would be only be limited to the side chains as such. Okay, so now again let us go to this color type, color menu, and let us now color it by type. Okay, now what has happened? Something interesting has happened. Okay, so this command, when I go to this color and I again colored it by type, well, what this command has done is that it has recolored all residue according to their chemical types, as you can note down over here. Okay, note that it colored only the side chains because in your control panel you have made the changes in such a way that coloring would only be affecting to the side chain, and the backbone, as you can see over here, is still colored in yellow. Okay, okay, now you can see over here that non-polar side chains are now gray in color. Other side chains are not shown. Okay, why? Because you have selected and displayed only non-polar amino acid residues. Okay, now take a look around at the control panel to see the colors assigned to other residues. Okay, other type of residues to be precise. Now you should notice the color for basic amino acid residue is shown in blue, while the color for acidic amino acid residue is shown in red. Okay, so uh, this positive amino acid residues, positively charged amino acid residues are basic amino acid residues, and they are shown in blue color, and acidic amino acid residues are shown in red color over here. Okay. So now one more thing that you should note. Well, let us rotate this molecule. Okay, and you should notice that most of the gray side chains, the side chains that are colored in gray, okay, that are currently on display. Well, their orientation is generally towards the core of your molecule. On the other hand, your non-polar side chains that are now shown in gray color, well, they are somehow oriented towards the heart of your molecule, as you would expect. Okay, why is that? Because most of the hydrophobic side chain should be buried deep inside the core of your protein. Okay, and most well, that is how protein folds, right? Protein folds properly when it kind of orients its non-polar side chain towards the core of your protein, and polar and charged amino acid residue side chain are usually present on the surface of the protein as such. Well, life has, kind of manage this problem of placing hydrophobic and hydrophilic amino acid residues appropriately, so that your protein would become thermodynamically stable in its surrounding cytosol, which is usually, the proteins are usually covered by um, are usually surrounded by water molecules when it is present in cells, right? So now you can see that non-polar amino acid residues are oriented towards the center of your protein. You would see that none of the non-polar amino acid residue is is present on the surface of protein. That usually don't happen. Okay. Now let us see what is the case with this positively charged amino acid residue and negatively charged amino acid residue. How they are oriented, how their side chains are oriented. Okay. So now let us see let us now select the uh, amino acid residue that has got acidic side chain. And to do so, you can do by going again to this select command. Go to this select, then you can go to this group property, and you can now select acidic amino acid residues. Okay. Now when I click on this acidic, note what things would change in your control panel. Currently, only the non-polar amino acids are selected. And when I click on this acidic, the selection has changed to only acidic amino acid residue. So now note that non-polar residues are now unselected and only the acidic group are selected. Okay. So this would also indicate that whenever you use this select and any command from group property or group kind, so every time you use this command, it would select new amino acid residues in your control panel, leaving what you have selected in your previous command as such. Okay, so now what if you want to select acidic as well as basic amino acid residue at the same time? Okay, for time being, we have only selected acidic amino acid residue, and now we want to add basic amino acid residue to our previous selection. For doing that, what you are supposed to do is that you are supposed to hold on to this control button on your keyboard, and keeping that control button push, you can again go to this select, then again go to this group kind, and now select basic. And when you select this basic, your basic amino acid residue would be added to the selection as I would show you now. Okay, now you can see that acidic residue are selected as well as basic residues are also selected. So if you use this control command while selecting the selecting amino acid residues or some another selection, pushing the control button would add to the selection without unselecting the previous group that you have selected. Okay, so now what we have done, we have selected acidic as well as basic amino acid residues. Okay, this is what we have done. So first you have selected acidic amino acid residue, then you have pushed the control button, and then again you went to the select command, and on the second command, when you press the control key first and hold it down while pulling the selection menu. So by using this control with select menu commands would add groups to the selection without unselecting the others. Okay, so now what we will do, we would again click on this side button. Now you would see that when we click on this side command of your control panel, it would display only acidic and basic amino acid residue. Well, let us click on this now. Okay, now what have you noted? What have you noted? That when you click on this side button, this has added side chains for selected groups, that is basic and acidic amino acid, and removed all other side chains. Previously we have selected non-polar, it has removed non-polar, and now it has added the side chains to basic and acidic amino acid residue. Well, now let us look around in our model now. Okay, so what do you see now? Most of the red and blue side chains are oriented on the surface of your protein. Okay, as you would expect for charge side chain in water soluble protein. Why? Because these charge side chain usually make contact with water molecule. Okay, now note that the non-polar side chains are no longer on display. Why? Because you did not hold down the control key during selecting group property acidic command as we have done a previous while. Okay, so that is what I wanted to show you in our in this representation, that your protein is said to be folded correctly when all or most of the hydrophobic amino acid residues are generally oriented toward the core of your protein, and charged residue like acidic residue and basic residue or even polar amino acid residues, their side chain should be oriented on the surface of your protein so that they can interact with the surrounding water molecule in order to make your protein molecule thermodynamically very stable. Okay, so this is what you have learned so far by simply coloring your protein molecule with different coloring scheme. Well, this is what I wanted to teach you people, to give you a different aspect of structural biology, to view your biochemistry with structural aspect. Okay, that is one of my objective of creating these video lectures. Okay, so again, well, let us select display and center the complete model with side chain. Okay, I have selected the entire model by clicking on this. Then if I hit enter, I would show everything, and if I hit on this side chain command, it would show you all of the side chains. Okay, now let us revert back to our coloring to backbone and side chain, because we would be needing to color backbone and side chain as well. Okay, so this is what it is. Again, what you can do is that you can go to this color and you can color by accessibility. Well, let us see what happens when we color our molecule by accessibility. Well, now you see that it has the coloring scheme has changed somehow. Now, well, let me tell you as to what exactly has happened. Well, let us discuss exactly first key what is accessibility. Okay, so when you color your model by accessibility, okay, you see the model is you see the model in colors that would range from violet to orange, as you can see. Okay. uh, Now what do this violet to orange color represent? Okay, you can see that some of the residues are colored in violet while some of the residues are colored in orange. Okay. So the color of each residue over here, as you can see, is based on the percentage of its surface area that is exposed, or what we call it as accessible to the surrounding solvent. Okay, so in this way, the least accessible, or what we can say a buried amino acid residue, are colored in a shade of violet, while the most accessible residue would be colored in a shade of red. Okay, so now to residues of higher accessibility, deep view would assign the colors of higher wavelength in the visible spectrum. Okay, therefore the color violet is about 400 nanometer and red is about 700 nanometer. Therefore, in this display, the colors of the rainbow, as you can see over here, now it is reflecting the exposure of residue to solvent. Okay, in other words, violet residues are least exposed, while red residue, or the residue that are in shade of red at least, the residues that are at least in the shade of red, as you can see over here, well, these are the residues that are most exposed. Okay, so now let me demonstrate you the concept of accessibility over here. Okay, so what we need to do is that we need to locate this trinag inhibitor and select it. Okay, so well, let me display it in solid 3D. Okay, and let me show this color. Okay, let me show it in its surface. Okay, now you can see over here this particular amino acid residue that is present on the surface. Therefore, it is most accessible, and this residue, the residue number NAG201, it is present, in the interior or the core of the protein where it is not accessible by water molecule. Accessibility, right? Therefore, it is colored towards the shade of blue, and green is present toward the shade of red in the visible spectrum. So in this way, you can easily kind of locate as to what residues are solvent accessible and what residues are solvent inaccessible. So you can see your inhibitor NAG, well, it has got a variety of exposure to solvent molecule. Some portion of your inhibitor is deeply buried inside your protein, while some portion of your inhibitor is present on the surface of your protein. Okay, so let us revert back to show it in wireframe. Okay, okay. So now, well, let us focus on some another residue now, right? Well, let me remove the surface of your protein now. Okay, now let us the cent select and center this tryptophan 62. Okay, well, let me tell you something called as option clicking. Okay, option clicking is something called as when you locate the tryptophan 62, then first right click and then left click. Okay, when you right click and left click on any residue, you said that you have option clicked it. Okay, so after option clicking this tryptophan 62, okay, the residue in the control panel can be option click. Okay, So now what we want to do is that we would require only this tryptophan 62 selected, okay, and the whole model shown as it is being shown now. Okay, now let us click on the surface button which is present over here. Okay, click on this surface header. Okay, so this surface header, it is a small cluster of dots, as you can see over here, with V shown over here, that corresponds to the van der Waal over here on the lower right of this cluster of dots. Okay, so in the control panel. Okay, so this tryptophan 62 is now shown with the, when I click over here, this tryptophan 62 would be shown. Okay, now once you option click it, the rotation of your molecule would be around the residues that you have option clicked. Okay, the center of rotation would be this selected residue, and if I use this zoom button, your tryptophan molecule would be now brought into the more clear picture. Okay, so now let me reorient so as to make my view very clear. Okay, so this is what it is, right? So now notice that this tryptophan residue whose surface is now shown in van der Waal, okay, as we have selected van der Waal over here. Okay, so notice that your tryptophan 62 lies just below the surface of the enzyme. Okay, so this residue is, you can say, it is buried quite well. Okay, surface of the enzyme, and this residue is almost completely surrounded by another amino acid residue or another groups, you can say. Okay, it is completely buried. Okay, uh, now I'm going to show you something really interesting. Okay, so do you notice over here that there is another triangle present over here on your surface menu? Okay, notice that over here just beneath the surface header there is a small black triangle that I am pointing to it now. Okay, so now this black triangle, is a handle for another pull down menu. If you click over here, another pull down menu would pop up, it would appear. Okay, so now when this pull down menu appears, you are supposed to click on the triangle to pull down menu and select accessible rather than van der Waal. Okay, so now if we select accessible, this V now has changed to A. Okay, now notice that this V has become A, that correspond to accessible, not for van der Waal. Okay, again make sure we are making sure that with the whole model on display but only tryptophan selected. uh, Now we would again click on this accessible button. Okay, see now what happens. Okay, V has appeared over here. Okay, so if I again click on this V, do you see what is happening now? Okay, a small region of surface dots appears and disappears. Well, now let me tell you what this small surface of dot represent. This you should note that this small surface of dots, it appears over your van der Waal surface. This is your van der Waal surface. Okay, and the few dots that you see over here that would appear and disappear, those are the accessibility of those that correspond to the accessibility of your tryptophan amino acid residue. Okay, so now this small stretch of surface that you see over here, this surface is that portion of your amino acid residue tryptophan that is accessible to solvent, or that is exposed to solvent. Okay, you can see that only a small fraction of your tryptophan amino acid residue is solvent accessible. Okay, so this is this is quite consistent with violet color that is assigned to your accessibility. Okay, so well, what I want to show you is that your entire tryptophan 62 is not solvent accessible, while it has got its own van der Waal radii. Okay, every amino acid residue will have its own van der Waal van der Waal surface, but that don't eventually mean that all of the residue would be exposed to the solvent. So, since our tryptophan 62 is buried in protein, only a small fraction of this tryptophan 62 is exposed to solvent. And to be precise, this is the small portion of your tryptophan 62 that is exposed to your solvent molecule. So there is difference between van der Waal surface and solvent accessible surface. Okay, and that you can identify using this accessibility, or you can say coloring by accessibility. Okay, so well, let me again define that what is the exact difference between van der Waal surface and your solvent accessible surface area. Okay, so van der Waal surface usually lies at the distance of the van der Waal radius from the center of an atom directly above its surface. And this van der Waal surface includes the full surface of all selected atoms except where the surface overlaps. In contrast, the solvent accessible surface will lie above each atom at the distance of van der Waal radius plus 1.4 angstrom. And thus, it would include only the surface with which a spherical solvent molecule of radius 1.4 angstrom could come into contact with. Okay, therefore, any other part of the surface is hidden from the solvent by surrounding residues. Okay, so like coloring by accessibility, showing the accessible surface might require some lengthy calculation that are needed to be done. Okay, so in some cases it might take some longer time duration to compute all solvent accessible surface area. Okay, so in short, what I want to express is that if this is your protein molecule, okay, say some side chain of your protein molecule, it will have some van der Waal surface. Okay, and it is not necessary that all of the van der Waal surface would be accessible to solvent. Okay, so the solvent accessible surface area is the area that is, what we do is that we take a sphere of 1.4 angstrom unit radius and we rotate it on the surface of your van der Waal radius. So wherever this sphere would come in contact with, that much area would be the uh, solvent accessible surface area. Okay, why 1.4 angstrom sphere? This 1.4 angstrom is the radius of your water molecule. Okay, your water molecule considered as a whole, it has got a radius of 1.4 angstrom. Therefore, if we consider a sphere of 1.4 angstrom and roll it around the van der Waal surface, so wherever this water molecule rotates or wherever this water molecule slides, that much area would be solvent accessible. That is what the concept is. Okay, now let us turn off both the van der Waal surface. Now we are turning off the solvent accessible surface area, so this dots would go off. Then I would again select this van der Waal radius and again turn off the van der Waal radius by clicking on this visualization button over here. In this way you have turned off both van der Waal as well as solvent accessible surface area. Well, now let us center the model. Okay, and it is let us keep it still colored by accessibility. Okay, so now, well, let us, I will show you one more interesting thing so far the coloring is concerned. Go to this display menu and select this slab, display, and then slab, and see what happens over here. Display and slab. Okay, so when you use this command from this display menu, or when you use this slab command from display menu, this command would reduce the display to a thin slab that is that goes through the center, or you can say the slab centered at the middle of your molecule. Okay, so with this display of the molecule in cross section, you can see that residues in the heart of molecule are not accessible to solvent. Okay, by taking this slab, or you can say by taking the transverse section of your molecule, okay, what you are looking through is the cut of your molecule. If you cut your molecule right from the center, this is what you would see. And what is that you are noting now? You can see that the residues in the core, or you can say the heart of the molecule, are usually not accessible to the solvent, and hence they are colored in a shade of dark blue or violet. While the residues that are present on the surface of your molecule, that are more accessible to solvent, and therefore those are colored in towards the red spectrum, red of your spectrum message. Now if you kind of rotate your molecule, you would notice that whatever molecule appears at the center of your cross section are always in a shade of blue, and whatever residues that are present on the surface, those are always toward the towards the towards the red side of the spectrum. Okay, so if you are still not getting what this means, what we have done is that we'll say if this is your protein molecule, and when you took slab, okay, this is your center of your molecule. If you cut your molecule from the center and see it in and rotate it, you would see, if you rotate, cut and rotate, you would see that you would get some transverse section. Well, say for example, let me take an analogy of apple. Okay, now if you cut this apple in the middle, what you would see? You would see something like this, right? So this is what we have done. So after taking slab, you are looking at the transverse section of your protein molecule. Okay, now I will show you, you can remove the slab towards this side, as well as you can move your slab towards the other way around. Okay, so you can take thin cross sections like this by moving the slab away or towards you. Well, let me show you how these things might work. Okay, so what you can do is that you can also move the slab towards or away from you, so that you can take thin cross section of your molecule. Okay, and in order to do this, okay, in order to do this, you can use well, say for example, if this is your protein molecule, right, and you can use the shift key to drag shift, you can use the shift key on your keyboard. You can hold the shift key and drag the mouse up and down in order to uh, in order to in order to shift your cross section towards you or away from you. Okay, if I click this shift, or if I hit the shift button on my keyboard and then drag my mouse up, that means I have moved my cross section. Outside this molecule in this direction. Okay, now again I would click on the shift button and scroll down. I can get back to the center, or you can use this to zoom center to again go to the center for over here. Okay, what you can do is that again you can push this shift button and scroll upside. So that would mean that you are moving through cross section towards this direction. Okay, again shift, again push your shift and scroll down. You would be moving your cross section towards you. Okay, and if you use this zoom center, you would be taking your cross section to the center of your protein molecule. Okay, now doing this, what you can learn. Okay, so these slabs are very handy for eliminating the background and foreground groups that might appear when you try to do some structural analysis. Okay, by using slab, you can expose only the groups that you want to study, or only the amino acid residues that you would like to focus. Okay, so let us now focus on small colored squares at the right hand column of your control panel. Okay, this I am talking about. Okay, so the small colored squares at the right hand column of the control panel provides a means to color individual residues, while the word color that I have mentioned at the very beginning of this lecture. Okay, this word color at the top of your control panel will allow you to choose a color for all selected residues. Okay, so now let us use this thing. Well, let us display the whole model with the side chain. Okay, and select all group except trinag. So how can you do this? Okay, there are several ways. One of the easiest way is that you can first select this trinag and then go to the select and use this inverse selection, so that you have selected all the residue except trinag. That is what we want to do. Okay, then what we will do now is that we would color the selected residues. Okay, uh, whatever we have selected over here. Okay, if you click on this heading color, okay, a standard color will bar would appear over here. Okay, so now you would see that there are a lot of coloring options that are shown over here. From where we have obtained this? By hitting this color menu over here in your control panel. Okay, so now what you can see over here, that there is a shade bar as well. You can adjust the shade bar as you wish, depending on what kind of shade do you want. Okay, so if necessary, slide the pointer on the bar to give the brighter color of the spectrum. Right, you can use either brighter or you can use the darker color. Okay, so well, now for our case we would want this green color. Well, let us use, say, some dark color of green. Okay, by decreasing the shade color. Okay, and if I click OK, now you can see that all the residues that are selected are now colored in the shade of green. Okay, well, now let us come out of this slab command. Okay, So now we need to select this trinag is still colored by accessibility, right? So now we want to select only the inhibitor. So how we can select only the inhibitor? Again, we can go to select and then select this inverse selection. So now only trinag is selected. If I use this color menu, maybe I will color this inhibitor in a shade of red. Okay, now what representation you have created? So selecting this bright red, okay, color of bright red for trinag, what you have done is that you have shown your enzyme in green color and your inhibitor in red color, right? So all I want to demonstrate is how you can use this color menu over here. So uh, coloring by this particular menu would color only amino acid residues that are selected, while if you use the color menu from the main toolbar, it would color all the model, the entire model as such. It would completely be dependent on you as to what you want to color. Okay, so besides this, you can also color the individual amino acid residues by using this green box, by this box over here. If you click on this box, we can color the amino acid residues as by our wish. Well, let us color the last amino acid residue by yellow. Okay, so let us select this leucine 129 and color it by yellow. You can see that the last amino acid residue has been colored by yellow color. Okay, so the C terminal amino acid residue is now colored by yellow. Okay, well, now let us revert back our coloring scheme to CPK. Okay, now you can go to color, and if you color by CPK, everything would again revert back to the normal CPK representation. Okay, so now do you see that there are some yellow colored things in your protein molecule? Okay, do you see these bonds that are colored in yellow? So now let us identify what these yellow things are. Okay, for this what you need to do is that you need to click on the fourth icon from the right. Okay, so on this graphics window, it has got an eye with four arrows towards a dot. Okay, so if you click over here, it would ask you to pick some atom. So now if you want to identify what this is, okay, you need to click on any of the atom. And you know, whenever you click on such an atom, when you use this function, the corresponding amino acid residues is selected and the center of rotation is usually placed around the selected atom as such. Okay, now since this is the center of our molecule so far, you can zoom on it and identify whether it is still yellow color or not. So this is cysteine. Okay, now again let us see what is the second cysteine, second atom in yellow color. You again use the same function. First we have selected cysteine 6, and then if we click over here, this is cysteine 127. Okay, so this atom belong to cysteine 6 and this atom belong to cysteine 127. So now based on this data, we can clearly say that this yellow bond that are shown over here, yellow colored bond, are those that correspond to the disulfide bond that are you know that are that stabilize your tertiary structures. These are called as disulfide bonds. Okay, okay, now let us select all. Okay, so that everything is selected. Let us again color it by CPK. Okay, Good. So now you can kind of, you know, see as to what is the colored molecule. So the yellow colored bonds are those that correspond to your disulfide bond. Okay, now I have got an assignment for you. Okay, what you are supposed to do is that you are supposed to make a model. I would show you your assignment. Okay, you are supposed to create this representation. Okay, you are supposed to make a model in which your lysozyme is shown as ribbons colored by secondary structures, and trinag is also shown in normal CPK with dotted van der Waal surface. Your model should look something like this, but in it might be in some different orientation. Okay, now you should note that in this representation the ribbons are shown, the ribbons are shown in series of lines. Okay, these ribbons are shown in series of lines and there are 5 lines in each ribbon. Okay, so you need to make such representation. I would give you a hint to make your job easier. You might have to play around and find correct settings to display ribbons in form of these 5 lines. Okay, so I would expect your assignment to be present in my inbox. Okay, so this is your assignment. Okay, well, now let us move on to our next portion, that is measuring and labeling. Okay, for measuring and labeling, again let us go back to our SPDBV, okay, and to our protein molecule. Well, let us select, display and center the complete model. The entire model is select, displayed and centered. Okay, and well, let us color the entire model by CPK. Backbone as well as side chains are colored in CPK. Yes, now we are ready to go for our next ride for measuring and labeling. Okay, now this measuring and labeling can be done using these commands, as you can see over here. To the right movement, to the right of this movement button, these are all movement button. This is rotation button, this is zoom button and this is translate button. To the right of this movement button you have got this measuring tools, you can say, or measuring buttons. Okay, so this button number 5, 6 and 7. Okay, 5, 6 and 7. Okay, so this is for, this button is for measuring distance, this button is for measuring bond, and this button is for measuring dihedral angle. Okay, well, now let me tell you as to how do we measure the distance between any two atoms. Click on this button. Okay, after clicking it has turned black. That means that this function is active now. Okay, and once it becomes black, it would ask you to pick any one atom. So let us pick this atom, and then it would ask you to pick second atoms. Let us click this atom, and when you select the second atom, it would show you what is the distance between the two picked atom as such. Okay, and again it would ask you to pick another atom. So in this way continuously you can go around, you know, picking the atom and finding out what is the distance between the two atoms as such. Okay, you can again click on this atom to come out of this function, or you can use this escape button on your keyboard to come out of this function. So now if I click or if I hit this escape button on my keyboard that I am doing now, I can come out of this function. Okay, so this is how you you know, find out what is the distance between two atoms. Okay, so now you can remove this uh, this distance as well. So now to remove the distance that you have calculated, what you can do is that you can go to this display, then labels, and then use the clear user labels. You can use this option. Okay, if you select over here clear user label, so whatever measurements that you have made so far, everything would go away. So this clear user labels from this display menu, okay, uh, it is, you know, these user labels, whatever measurement that you yourself do are called as user label. Okay, and it is mean to distinguish the user label from the group labels that you usually implement or you usually put forth by using this label menu from your control panel. This is different and what you do is different. So whatever you do would be included in user labels. Okay. So now what is the application? Well, you know, using this measure button, you can, you know, find out the exact dimension of your protein molecule. Well, let us click on one end of your protein molecule and the corresponding another end. Okay, so you can see, and let us come out of this function. Okay, so you can see the length of your lysozyme molecule is around 45 angstrom, and the width of your lysosome molecule might be around 25 angstrom, as you can see over here, right? So this is how you can measure the distance between two atoms and find out the overall dimension of your protein molecule by using this simple measure distance command. Okay, so now let us move on to the next button. Okay, so let us kind of come out of this function. Okay, display labels, clear user label, that would clear out all of your work. Okay, so now let us select display and center the entire model. Okay, now let us see how you can use this angle button. So this button is meant for using the for finding out the angle between any three atoms in your protein. Okay, so for that, the first selection that you make would be the central atom, and the next two atom that would pick would be the corresponding atoms, you know, that are attached to your central atom. Okay, so this is how it works. If you want to find out the angle between these three atoms, you would first have to select the central atom and then the two atoms that are connected to your central atoms. And your SPDBV or deep view will give you an idea as to what is the angle between these three atoms. Okay, so let me demonstrate you. Well, let us find out what is the angle between these three atoms over here. Okay, so the first atom that you need to select is the central atom. I have selected the central atom. Now it is asking me to pick the second atom. Well, let me pick this one. Now it is asking me to pick the third atom. Let me pick this third atom over here. Now the angle between this atom, and this atom is 141 degrees. So this is how you use this measure angle. Okay, so if you again click on it, you can come out of its function, go to again display labels, and you can clear your work. Okay, so in similar way you can use this button for finding out the dihedral angle of any four atoms. Okay, okay, do you see this leucine 41 button over here? You can use this button to know the identity of any molecule. Okay, so if you click on this button and you want to know as to what is this particular atom, and if you click on this atom, you would know the identity of this particular atom, that this atom that you have clicked is the C alpha carbon atom of residue glycine 170. Okay, so you can continue labeling this way to know what are the amino, what is the atom that you are dealing with, right? So in this way you can identify a particular atom in your protein molecule. Okay, now one more thing that I would like to clarify is that your rotation or your movement buttons are disabled when you use any of this function. Therefore, make sure that whatever atoms you want to click are in proper view before using any of this function. Look, you cannot rotate your molecule. I am trying to rotate my molecule now, but it is not possible. So unless and until you come out of this function, you cannot rotate your molecule. So make sure that the two atoms that whatever you are working on, when you are using these function, well, they are properly visible. Then and then go to this function and use this particular uh, selection for finding out the distance or whatever you want to do. Okay, so you can remove all of your work in the same way as go to display and labels and clear labels. It would remove all of your work. So this is, my friends, how you can color your protein molecule, how you can measure your protein molecule, how you can label the amino acid residues in your protein molecule. So you can label these ways as well. Okay, so in this way we have completed our basic exercise in protein structure visualization. Okay, and I hope you have learned some important things and you are enjoying this visualization session. Okay, so see you guys in our next lecture.